This is 0. Okay? Actually, we don't need that. I'm sorry. I mean, we can do it this way, but this is longer. We don't need that. Just substitute x equals b here. Substitute x equals b here. So you get u gamma wake at b, and this guy from b to b, it vanishes. So you get these guys balance each other. You get this equation immediately. Okay? And which means I have to add here equal. So from here to there, this is a free wake. This is free wake. From here to there, yes, I substitute x equals b. And I'm saying that this is the condition. Because you said that delta P at the trailing edge is 0. Okay? So anyway, we got this relation, which relates what? It relates the wake circulation distribution to the total bound circulation. Okay? The wake circulation distribution at the trailing edge to the bound circulation. But yeah, you said this is at the trailing edge. We want to establish a relation between gamma wake at any point and gamma bound. So you got now gamma wake at the trailing edge, but I can't relate gamma wake at the trailing edge to gamma wake at any point. Right? Gamma wake at the trailing edge at B is gamma wake at any point x and what? So at the trailing edge, it will be later at x at a later time, right? So this time plus the time taken to travel from B to that location x, which is distance divided by the free stream. Okay? Any question about that? So this is negative gamma dot B. Any questions so far? So let's see what he did. This is very straightforward, no penetration boundary condition. We got two unknowns. So we need to establish a relation between them. We're almost there. But at any rate, this is very hard to proceed. And the guy immediately introduces harmonic motion. So here we have, if we do harmonic motion here, so let me bring it again, just not to confuse you. So far everything here is generic. Here is the equation, negative 1 over 2 pi, gamma bound of x and t, x minus whatever, x prime, dx prime. The same here, 1 over 2 pi. This is from negative b to b, but here is from b to infinity, gamma wake, x prime and t, dx prime, x minus x prime. This is the v motion at this x and t. Okay? This is the no penetration boundary condition. We have two unknowns. Now the guy said harmonic motion from the get-go. So harmonic motion, your input, you're given now, which is a function of x and t, is some complex number, maybe v bar of x, ei omega. Okay? So when you apply something here, cosine and sine omega t or ei omega t, because the equation is linear, anything on the left hand side will also be an ei omega t. So this, because of linearity, if any variable in the problem will be, so this is gamma b bar ei, this is of x, ei omega t, gamma wake is gamma wake bar ei omega t, anything, log the large gamma, which is function of time only, this will be constant, this is a constant, ei omega t and so on so, right? Yes, Anshad?
For gamma wake of z, are you saying that it's a function of both x and y?
Where? No, I'm sorry, I'm using x and z interchangeably, so z here is dummy variable for integration, so it doesn't matter. No, it's just the real axis. In reality, yes, it's function of x and y, but you would not be able to get analytical results out of that. Okay, so this means what? This means that actually everything here will be times ei omega t, so you can take it as a common factor or divide by, so this guy, all the t dependence will go away and you end up with just having bars here, right? The spatial quantities. Any question about that? Any question? Okay, so like I said, we need to relate gamma wake to gamma bound. You already did that, so I will try to get gamma wake bar from here to put it there. So this equation, here is the left hand side. If this is gamma wake of x and something, so it is gamma wake at that x, e to the I omega times the whole time, which is t plus x minus b over u. This is equal to, this guy is here, differentiated with respect to time, you get I omega. So I omega gamma ei omega t. So you can just remove the ei omega t with each other, and you end up with gamma wake of x is, there was a u somewhere, right? So yeah, there was a u here, u here. This is the relation, u times gamma wake at t. So we have u here. So if you divide by u, we have omega, you can multiply and divide by b to get k. Remember, k is omega b over u, right? Ik gamma bar e to the ik e to the negative ik eta, where eta is x over b. And we have b here. So just to lump things together, this is your equation, we're done. But to lump things together, Schwarz called this Schwarz called this omega, okay? Anyway, so it's the circulation, it's the amount of circulation. So we got the wake circulation distribution in terms of the total circulation. This is just a number, but this is a function of x, okay? So can you tell me what's the next step? What should we do now?
Step.
I'm sorry?
Step.
What's the next step? Okay, we got this gamma wake as a function of total bound circulation. What should we do? I'm sorry? Yeah, exactly. We had an equation here. The blue equation was waiting for a relation between gamma wake and gamma bound. I'll take this guy and put it there. Okay? So I'll write it in blue as well. So the blue equation says that 1 over 2 pi, I'll just multiply by negative. And maybe we will normalize negative 1 to 1 gamma bound bar of zeta, or let's write it as eta, divided by zeta minus eta d eta equals what goes in the right hand side, this guy and the v motion. So negative of the v motion, which we call it v bar, right? We call it v bar of x. Now it's zeta. And this guy was here in negative, goes in positive, and we multiply again. 1 over 2 pi from 1 to infinity. Gamma wake bar, which is here, negative I k omega e negative I k eta. So just to make sure, this is zeta minus eta.